We're following up on a triple integral example where in the first video I set up triple integrals in rectangular and cylindrical form to be able to measure the moment about the xz plane with a specific given density function. And our region, algebraically, is inside of a sphere, x squared plus y squared plus z squared equals 20, such that z is greater than or equal to x squared plus y squared, which would be inside of a paraboloid, or a parabola bowl, as I like to nickname it. In this video, we're going to look at it in spherical coordinates. This is a little bit more interesting. I will also volunteer that you probably wouldn't choose to use spherical if you were trying to find what's the most efficient way to evaluate this. I just want to look at this region in spherical coordinates in case there were some moment or other calculation where it would turn out that spherical is superior. So, some reminders. The region itself looks something like this image here, and it's inside of the sphere but within the bowl. We were able to show that this circular top view is a circle of radius 2, and the side view looks a lot like a parabola, and we're going to use that information to assist us setting up the boundaries for the spherical integral as well. But remember, whereas rectangular and cylindrical, you could kind of separate the xy plane and look at the z component separately. That's not always the case with spherical. In fact, many times it is definitely something you have to look at a little bit differently. So, quick little reminders. The top view of our little region, let's see if I can get this all to fit here, is a circle of radius 2, and we already knew that in this particular case theta was from 0 to 2 pi, and that means it's rotated all the way around the z-axis. And for this problem, we don't need anything else out of the top view. The side view is going to be used to help us determine the angle phi and the radius rho. We're going to use the side view for that. So where this is the z-axis, this is the y-axis, and the x-axis would be coming and shooting straight up at the camera from there. Now these pictures are a little bit small to work with, so I'm just sort of setting up the problem to be solved. Theta is fixed. Theta goes from 0 to 2 pi. That will not change. But what comes with these two variables will be slightly more interesting. So here we go. If we were to look at the side view, and I don't think it'll all fit in one screen at the same time, it gets close. I'm going to focus up here. Remember, the angle phi is measured from the positive z-axis, and as you go downwards, pi over 2, pi would be the maximum. So phi starts here and goes downwards. The reason I have not shaded the entire region in is for a simple reason. From here to here, from the origin to here, is the radius of the sphere, which is the square root of 20. And as we work our way downwards with this angle, once I hit this point where the paraboloid intersects the sphere, I'm no longer touching the sphere as I fall below this. So in this particular part of our graph, the radius rho goes from 0 to the sphere, which would be probably better to say 0 to square root of 20. but I don't know the angle for that. I know that phi goes from 0 at the z-axis to some mystery angle at this place here, but I have to determine what that angle is going to be. I'll come back to it in just a moment. Once I pass this threshold, the region I'm looking at is it's just a little sliver where the radius rho from 0 to wherever it touches the paraboloid, and I need to get algebra for that. I don't have algebra for that yet. It's got to be solved for rho equals. And the angle phi, let's come down here a little bit further, is going to start at that mystery angle, which I did not find, and it's going to go all the way into pi over 2. So mystery angle to pi over 2. I'm taking little chunks of understanding and leaving spots for the places where I need to fill in the blanks afterwards. Now, some of you might be wondering, why is he not shading in the left side? I mean, doesn't the graph have all of that? I mean, look at the graph. It's got a right side, it's got a left side. Well, the answer to that is you cannot think about sides when you're in coordinates that are not left and right and up and down. What covers the entire rotation around the z-axis is the fact that theta is going to rotate all the way around. So if I had some really cool animated software, which some very high-end channels support and show, this is going to get rotated all the way around the z-axis. Theta will do that for us. I just need to accomplish this little fact. If the 3D graph were to change on the backside, well, then that would be a more interesting integral that is more than we're going to spend time on probably in this course. Sounds like fun to me, but it's a little bit beyond what we're going to have time to do in the short time we have to study triple integrals here. Now, what shall we do first? How about the angle phi? We discovered in the first part of this video that the top view was a circle. Again, let's remind ourselves, there's a circle here, and that circle had a radius of 2, and it happens when z was 4 units above. The link to that's in the description. You can go back and relive that excitement. So I can look at this right triangle and say, well, that the tangent of phi is equal to the opposite, which is 2, over the adjacent leg, which is 4, which is 1/2, and that for us means that this mystery angle is either the inverse tangent or the arc tangent of 1/2. Arc tangent 1/2 or tangent inverse 1/2. I prefer the arc notation as a teacher, but as a student I honestly don't care which one you use. Those are boundaries, folks. In that first set of triple integrals, rho is going to go from 0 to the square root of 20, and phi is going to go from 0 to arctangent 1/2, and theta was 0 to 2 pi. In the second set of integrals, which, oh yes, because it takes two different types of radius to include the entire region, I have to have two sets. I know that the angle phi begins at arc tangent 1/2 and it goes to pi over 2, but I now need to figure out what is the radius rho. What is that going to be? Well, we know the paraboloid z equals x squared plus y squared, or z equals r squared. In spherical coordinates, z is equal to rho cosine of phi, and r is equal to rho sine of phi, and we'll square that. So rho cosine phi equals rho squared sine squared of phi. Now, if I divide both sides by rho, I will lose one factor of rho, which is my goal, because I need to solve for rho equals. Remember, if rho were to be equal to 0, we'd be looking at the origin only. So we're not going to be breaking any math rules by dividing both sides by rho. We're going to end up with rho is equal to cosine of phi over sine squared of phi, and it turns out that this is the paraboloid. Now remember the angles that we're looking at. If sine of phi is 0, we'd be dividing by 0. That's a problem. Well, the sine of an angle somewhere in the first quadrant is not 0, and the sine of pi over 2 is 1. Our phi values will work well with these boundaries. We won't be in any kind of trouble there. So that means this is our rho equals boundary is cosine phi divided by sine squared phi. Now, using a small little screen that we have here to try to capture everything is rather difficult with some of these problems. You have to use pause and write notes more frequently than you would if we had a giant board and you were sitting in a classroom looking at me writing on the board. But I think we have all the details we need now. I think we have the pieces that we're going to require. So let me just slide this over. Let's see what I can find. One more piece of the puzzle. The moment about the xz plane is what we're trying to compute, is equal to y multiplied by the density function, and the density function is given x plus z plus 5. Nothing actual engineering was considered in writing this density function. In fact, I think it's a little bit make-believe. But I'm working on developing, do you know what the substitutions are for the various variables with my students? And so that's kind of my modus operandi. And if you're curious about why I decided to add a number at the end, I'll tell you without explaining. It guarantees that the density will never be negative in my particular region. So now, here we go. Y multiplied by density will be equal to the following expression if you complete all the spherical substitutions. This here, students, is going to become this part of the body of what's inside the integrals. But don't forget, when you convert dv to spherical, there's also a rho squared sine of phi, d rho, d phi, d theta. So the actual body of the integral is going to look rather beefy. And so I'm now going to gather information from the last 2 pages and just jump right into a typed out solution, because honestly, if you saw me write this out by hand, I don't know if you'd be able to read it all. I'm hoping that you'll have a better chance here. So here we go. Zero to 2 pi is the theta part of the region. 0 to arctangent 1/2, 0 to square root of 20. those boundaries take care of this part of the picture, but not this little sliver right up against the parabola bowl. The body of the integral, rho squared sine phi d rho d phi d theta, plus another triple integral that captures this little sliver rotated around the z-axis, 0 to 2 pi, the new phi boundaries, the inverse tangent of 1/2 to pi over 2, and oh, where did this come from? Well, cotangent phi, cosecant phi is what I call this dilemma. Which one do you want to write down? Cotangent, cosecant, or cosine over sine squared all of phi? I chose to write it without the fraction, so it would be more readable, and the same body of our integrand. It would take these two together to calculate the moment about the xz plane. So do you see what I'm saying? For this particular region, this might not be the nicest triple integral to use, but I wanted to see what could we put together with the tools that we have. I think it's totally within our skill set. Hope you have picked up a few new little details than you would have before, and as always, until next time.